Another example of wave interference is called diffraction. Diffraction is just, again, a constructive superposition or destructive superposition of waves from different sources, and that creates a spreading or a modulation of what would ordinarily have been a plane wave, but it's now through a single slit. If you look at an example like this, where a plane wave is coming in from below and it hits a barrier where the barrier has a single opening, plane waves passing through that wide slit continue to look like plane waves. In other words, they still look straight across and they have the same spacing. But as the slit narrows, the pattern changes a little bit. Notice what's happening out here at the edges. There's a certain warping of the plane wave. And as the slit narrows even further, that modulation happens even more dramatically, because not only is the plane wave becoming a circular wave, notice what's happening to the amplitude of the wave. Here the amplitude is very large. Here it's somewhat large. You can see there are some crests and troughs, but there are some bands that are happening. And the bands are where the wave amplitude is getting really small. That's what happens when the wavelength, the barrier gets even narrower in size. The effect of the slit gets stronger as the slit gets narrower and gets close to the wavelength itself. So here the slit width is about yay large, and notice that that's going to be fairly comparable to the distance between crests, or the wavelength of the incoming wave. All these effects get stronger when the wavelength gets comparable to the aperture that you're passing through. So this is called diffraction, and diffraction is seen in lots of different kinds of ways. Here's an example where there's water waves, and so you see waves coming in from the bottom and heading toward the upper left. Near the shore, there are two rock formations that are making a barrier. So notice what's happening in between. The plane waves coming in now become circular or spherical waves as they pass through the narrow opening between the rocks. In other words, it's been diffracted. There's also an interesting pattern where there's a diffraction visible around the left-hand side of this rock, and in orange I've sort of highlighted the circular waves passing now around the left-hand side of the rock. Notice that those are meeting the diffracted waves coming around the right-hand side of that rock. So there's actually kind of two barriers here, or two edges. Radio waves sometimes get diffracted as well. If you think about what AM radio is, AM has frequencies on the order of 500 to 1,000 kilohertz on your dial. And if you remember that the velocity of a wave is always equal to wavelength times frequency, and here the speed is or velocity is c, then AM radio has wavelengths on the order of 300 to 600 meters, so it's pretty big. Such wavelengths can be comparable in size to the geographic features like hills or valleys that they would encounter as they're going around to try to get to your house, and so they would actually diffract. Other kinds of radio waves, like FM radio, has frequencies on the order of 100 megahertz, so substantially larger, because the highest AM frequency is only 1 megahertz. And again, since V equals lambda F for all waves, then FM radio would have a wavelength on the order of 3 meters, so very, very small. In this case, the features that you would be passing by if you were an FM radio wave are pretty large compared to the wavelength. And so in that case, the diffraction effect would be very small. You would not see bending of radio. So it turns out if you're in your house and you're down at the bottom of a valley, you're more likely to hear AM radio than you are FM if the antenna or the sender signal is way up on the top of a hill and you don't have line of sight. So there's a formula that we all have to know for diffraction, and that is if you have a plane wave coming in and hitting an open slit, there are going to be maxima and minima created as a result of each space inside of this slit looking like a little point source. So this place where my cursor is right now looks like a little point source. That looks like a little point source. That looks like a little point source. And if you imagine the point source that's coming from this edge of the slit and that one, now imagine that these make circular waves coming around. And once again, you'll have regions of nodal lines, that's right here, and antinodal lines, that's right here. If you were to have a second screen over here on the right-hand side of this diagram, you would have maxima, or constructive interference at certain locations, and you'd have minima or destructive interference showing up on the screen at certain locations. The opening of the size of the slit A creates the circular waves coming through the opening, and the antinodal lines will result in will come whenever crests start to overlap. Of course, nodal lines occur when crests meet troughs. There's an equation that we should know, and that is that the nodal lines, the places where complete destructive interference occurs, occur at certain angles off of the center axis when the following equation holds. A sine theta is m lambda. In this equation, A is the opening of the size of the slit. So that's the opening in the first barrier. Theta is the direction off of the center axis. Now actually this little dotted line here shows an antinodal line, so that's actually up here where constructive interference occurs. But at particular angles theta, where A sine theta is a multiple of the wavelength of the incoming wave, then I get destructive interference, and that would describe the nodal line, or the place of destructive interference along the screen. So the minima occur when A sine theta is m lambda, and then maxima occur approximately halfway in between the minima. To see the diffraction effect, you need A again to be comparable to a wavelength, or else the angles theta become really tiny. This is just like two-slit interference. You only get constructive or destructive interference whenever the apertures or the features of your experiment become comparable to a wavelength. For a chosen value of A, smaller wavelengths make the angles of the minima smaller, since sine of theta will equal a multiple of the wavelength over A. Notice as we go in this picture from red, which has wavelength on the order of 700 nanometers, to blue, which has wavelengths closer to 400 nanometers, the angles reduce in size because the minima are moving toward the central spot here. Instead of being way out here where the first minima is, it's way inside. That's to be expected from this formula of A sine theta is a multiple of the wavelength. Notice also what happens to the white light. If you send white light into a slit, and it's a small slit, then it starts separating into its colors because of the effect of diffraction. The red is being spread out more than is the blue. So diffraction is another example of constructive and destructive interference, and it's not taking place between two slits, but rather between the point sources of light coming across the width of a single slit. It has a single equation for us to know. A sine theta is m lambda, and that describes the locations of the minima, or locations of destructive interference for the light hitting a distant screen.